There are two ways to measure how fast the universe is expanding. The two methods are run by the most careful astronomers alive, using the best telescopes humanity has ever built. The two methods do not agree. They have not agreed for years, and as of April 2026, the disagreement is confirmed at the 1% precision level. The universe is either expanding too fast for the early universe to explain, or it was expanding too slow back then for the present universe to explain. One of those statements is true. Both cannot be reconciled, and this is only the first of 6 fronts on which modern physics is quietly cracking. Pour something warm, settle in, and stay with me, because what physicists say in public is not what they say in private, and the private version is much stranger than the news will ever tell you. Part 1. The two numbers that should be the same. There are two ways to measure how fast the universe is expanding. They should give the same answer. They don't. They haven't for years. And as of April 2026, the disagreement has been confirmed at the 1% precision level by some of the most careful astronomers alive, using the best telescope humanity has ever built. The conclusion is no longer something cosmologists can dismiss. The universe is doing one of two things. It is either expanding too fast, given everything we think we know about its early history, or it was expanding too slow back then, given how fast we see it expanding today. One of those statements is true. Both cannot be reconciled with the standard model of cosmology, and the standard model of cosmology is the framework underneath almost every news story you have ever read about the universe. Let me describe the two methods, because they are extraordinary in their own right, and the fact that they disagree is the kind of thing that, if you let it settle in for a moment, starts to feel like the floor moving. The first method begins with light that is older than every star you have ever seen. 380,000 years after the Big Bang, the universe cooled just enough that electrons and protons could finally bind together into hydrogen atoms, and at that moment the universe became transparent. Light that had been bouncing around in a hot, dense plasma was suddenly free to travel. That light is still traveling. We catch the leftover whisper of it with satellites in orbit, where it appears as a uniform glow at microwave wavelengths from every direction in the sky. We call it the cosmic microwave background. Reading its tiny fluctuations is like reading the birth certificate of the universe. If you plug those fluctuations into the standard model of cosmology and ask what the expansion rate today ought to be, you get an answer. The Planck satellite, in 2018, gave the best version of that answer, about 67.4 kilometers per second per megaparsec. That is a strange unit, so think of it this way. For every megaparsec of distance, which is about 3.26 million light-years, a galaxy is receding from us roughly 67 kilometers per second, faster than a galaxy that is 1 megaparsec closer. The second method is more direct. You measure the actual recession of nearby galaxies. You climb a kind of cosmic ladder, rung by rung, calibrating distances first with stars in our own galaxy whose brightness we know, then extending out to nearby galaxies using a special type of star called a Cepheid variable, then extending further with supernovae of a specific kind whose absolute brightness we can predict. At each step, you measure the distance, and you measure how fast that galaxy is receding from us. The slope of that relationship gives you the expansion rate of the universe right now. Adam Rees and the SH0ES collaboration have been refining this measurement for over 20 years. As of April 2026, working with the James Webb Space Telescope and the Hubble Space Telescope together, using a new method that combines Cepheids with red giant branch stars and carbon stars in a distance network architecture, the answer is 73.5 kilometers per second per megaparsec, give or take less than 1%. Sit with the contrast, 67.4, 73.5. The first number tells you what the universe should be doing today, based on what it was doing 13.8 billion years ago. The second number tells you what the universe is actually doing today, based on the galaxies we can watch right now. The difference is roughly 9%. In almost any other field, 9% is a rounding error. In cosmology, with this level of measurement precision, it is a 5 sigma disagreement. That is the same threshold by which physicists declare entirely new particles to exist. When the Higgs boson was announced in 2012, the bar was 5 sigma. We have crossed that bar in the disagreement between these two numbers. To translate the unit a different way, imagine a galaxy sitting about 326 million light-years from us. In Planck's universe, it should be retreating from us at 674 kilometers per second. In the SH0 universe, it should be retreating at 735 kilometers per second. That is a difference of 61 kilometers every second between two equally precise predictions of the same galaxy's motion made by the same physics community using two of the most expensive instruments humanity has ever built. The galaxy itself does not care which prediction is correct. The galaxy is doing whatever it is actually doing. The problem belongs entirely to us. We have built a model of how the universe behaves, and the model is telling us two different things about the same galaxy. For more than a decade, the working assumption in the field was that this had to be a measurement error. Maybe the cosmic dust between us and the Cepheids was being underestimated, blurring the distance ladder. Maybe the Cepheids themselves were being misclassified. Maybe the calibration to galactic standards had a subtle bias. These were sensible worries, and they are what science is supposed to do. You doubt the result. You doubt the instrument. You doubt yourself. The April 2026 result was the culmination of that doubt. The team used the James Webb Space Telescope, which sees in infrared light, to cut through cosmic dust that had blurred Hubble's view of the same stars. They combined 3 independent kinds of distance indicators: Cepheids, red giant branch stars, carbon stars, and linked them through a network architecture that lets any systematic error in one method get caught by the others. They pushed the precision down to 1%, the first time that has ever been done, and the answer did not move. The universe is, in fact, expanding faster than the early universe data predicts. The systematic error explanation is dead. This is what cosmologists call the Hubble tension. The word tension is gentle, almost diplomatic. Physicists chose it carefully. The other word that fits, and the word that is starting to appear in private conversations between people who do this for a living, is crisis. Here is one detail I find quietly remarkable. The distance network architecture, published in April 2026, did not just measure distances. It measured the same distances 3 different ways at once and forced the 3 ways to agree. Cepheid variables, which pulse with a period that depends on their intrinsic brightness, gave one set of distances. Stars on the tip of the red giant branch, which reach a specific brightness just before they fuse helium in their cores, gave another. Carbon stars in the asymptotic giant phase, with their own characteristic luminosity, gave a third. If any of these methods had a systematic bias, the others would have caught it. None did. The 3 independent ladders converged on the same answer with 1% uncertainty, using infrared light from the James Webb Space Telescope to verify what Hubble had been seeing in visible wavelengths. Every plausible escape hatch had been closed. What I want to do across the next 2 hours is take you slowly through what is happening, and I do mean slowly. Settle in. There is no rush. The point of this is not to alarm you. The point is to show you something that I think most people have never had explained to them properly. The Hubble tension is not an isolated anomaly. It is the first of many. We are going to walk through each one at a time, and watch them converge. By the end of this, you will understand why the title of this video is what it is. The shape of the story is something like a detective novel, where the detective realizes, halfway through, that every clue is wrong in the same direction, and the answer is not that one suspect was lying, but that the whole frame of the investigation is wrong. That is where the field of cosmology is right now. Most of the public does not know this, and the reason most of the public does not know this is the second half of the title. Physicists are not actually refusing to talk, they are talking. They are talking constantly, at conferences, in journals, in seminar rooms, in corridor conversations between sessions. The talk is different in those rooms from the talk you hear at press conferences. We will come back to why that is and what it says about how science actually works in a moment of paradigm strain. But first, I have to tell you how we got here, because the Hubble tension did not arrive overnight. It built slowly, over 20 years, while the field convinced itself that any moment now, the disagreement would dissolve. It didn't. It tightened. The graphs from the past 15 years tell the story by themselves. If you draw a chart with time on the horizontal axis and the measured value of the Hubble constant on the vertical, you see two trend lines that have refused to meet. The lower line, anchored to Planck and refined by smaller satellites and ground-based cosmic microwave background experiments, has stayed flat around 67, slowly tightening its error bars. The upper line, anchored to SH0ES and a growing set of independent late-universe probes, gravitational wave standard sirens from neutron star mergers, masers in nearby galaxies, lensed quasar time delays from the H0 LICAO collaboration, has stayed flat around 73, slowly tightening its error bars. The two lines run in parallel. They do not converge. They have never converged. The space between them is the space the field has been trying to explain away for 15 years. And to understand why that matters, you have to understand how the standard model of cosmology became the standard model of cosmology in the first place, is less than break time equals 1s, is greater than number, part 2, how we got here. The Hubble tension did not appear in 2026. It has been building, slowly and steadily, for almost 2 decades. The story of how the field came to know about it is, in some ways, a story about precision instruments. As our instruments got better, the disagreement between the two methods of measuring the universe's expansion rate did not fade, it sharpened. Each new dataset cut the error bars in half, then in half again, and the gap between the two answers stayed exactly where it was, becoming more statistically real with every iteration. For most of the 20th century, just measuring the expansion rate of the universe to within a factor of 2 was an achievement. Edwin Hubble's original measurement in the 1920s was off by almost a factor of 10 because his distance estimates to the nearest galaxies were badly miscalibrated. He thought the universe was about 2 billion years old. We now know it is closer to 14 billion. That kind of error was normal in early cosmology. It was a young field, working with primitive tools, trying to do something that nobody had attempted before, which was to measure the universe. The first serious modern attempt to pin down the Hubble constant, the parameter that quantifies the expansion rate, was the Hubble Space Telescope Key project in the 1990s. The whole point of putting Hubble into orbit had been, in significant part, to allow this measurement. By 2001, the Key project had narrowed the answer to around 72 kilometers per second per megaparsec, with an uncertainty of about 10%. That was, at the time, a triumph, a measurement of the universe to 10% precision. Around the same time, in 1998, two teams of astronomers working independently, one led by Adam Rees and Brian Schmidt, the other by Saul Perlmutter, were watching distant supernovae explode at the edges of the visible universe. They expected to see those explosions slowing down as the universe's gravity pulled everything back together. Instead, they saw the opposite. The supernovae were dimmer than they should have been, meaning the universe had carried them further than the standard model predicted. The expansion was accelerating. Something was pushing the universe apart, and that something had to make up about 2/3 of the total energy content. They called it dark energy, because they had no idea what it was. The 2011 Nobel Prize in Physics was awarded for that discovery, shared between Ries, Schmidt, and Perlmutter. I want to pause on what they actually saw. Type 1, a supernovae, are exploding white dwarf stars, and they all reach a very specific peak brightness when they detonate. By measuring how bright a Type 1 a supernova appears in the sky, you can work out how far away it is. By measuring the redshift of its light, you can work out how fast that distance is receding from us. Plot the two against each other, and you build a record of how the universe's expansion has changed over billions of years. What the supernova teams found, in galaxy after galaxy, was that the most distant supernovae were even dimmer than the standard model of the time predicted. They were farther away than they should be. The expansion had carried them further than gravity should have allowed. Either the universe had been speeding up, or the supernovae were somehow being misclassified across nearly half the visible universe. The expansion explanation won. The Nobel went to the people who refused to look away from the implication. Dark energy became part of the standard story almost overnight. Plug it into the equations as a cosmological constant, a fixed energy density throughout space, and the equations worked. You could now describe the universe with a remarkably short list of ingredients. About 5% ordinary matter, about 27% dark matter, about 68% dark energy, a flat geometry, a single number for the expansion rate. The model fit almost everything you could throw at it. Cosmologists started calling it precision cosmology. They were not being modest. The Planck satellite, launched in 2009, was the cosmic microwave background measurement that turned this from a model into a benchmark. By 2018, Planck had measured the temperature fluctuations of the cosmic microwave background to a precision that nobody 20 years earlier would have thought possible. You can take Planck's data, plug it into the standard model, and predict the value of almost any cosmological parameter you care about. The Hubble constant came out at 67.4, plus or minus less than 1%. At the same time, the SH0ES collaboration, led by Adam Rees, the same astronomer who had earlier helped discover dark energy, was using the Hubble Space Telescope to measure the Hubble constant directly from Cepheids and supernovae. By 2016, their answer was settling in around 74. The two numbers 67 from Planck, 74 from SH0ES, were both quoted with uncertainties around 1%. They simply did not agree. In the early years of this disagreement, the response from the field was patient. There were two error bars, both small, but maybe one of them was wrong. Maybe the Planck team had a subtle systematic in how they modelled the foregrounds, the radio emission from our own galaxy that contaminates the cosmic microwave background signal. Maybe the SH0ES team had a subtle systematic in how they classified Cepheids in distant galaxies. Each year, the error bars shrank, and the disagreement grew more uncomfortable. By 2020, the disagreement had crossed the 4 sigma threshold. By 2021, 5 sigma. That is the threshold at which physicists are supposed to start saying something is real. It is the bar that decides what gets called a discovery. The realization that the disagreement had crossed this threshold was the moment the language started to drift. In 2017, papers were calling it a discrepancy. By 2021, almost every paper was calling it a tension. By 2024, in private, you could hear people calling it a crisis. I want you to notice the careful gradient of those words. Discrepancy is something you might fix with a careful remeasurement. Tension implies that both measurements are probably correct and the model has to stretch to accommodate them. Crisis implies the model is wrong. The community has been migrating along that gradient for half a decade, and the migration has accelerated as the precision has improved. There is a peculiar tradition in physics around language drift. The same migration happened with the muon's magnetic moment in the early 2000s, when the wording moved from intriguing discrepancy to tantalizing tension to almost, but not quite, crisis. That story, as we will see later, ended with the anomaly disappearing into the standard model after a theoretical recalculation. Physicists watching the Hubble tension's vocabulary drift have been hoping for a similar resolution. The vocabulary has now arrived at a place from which no standard model rescue has appeared. The waiting is becoming uncomfortable. The James Webb Space Telescope arrived in late 2021, and its first scientific operations began in 2022. The hope, quietly held by some, was that James Webb would resolve the Hubble tension by showing that Hubble had been mismeasuring distances all along. The reasoning made sense. Hubble sees invisible and ultraviolet light. Cosmic dust blocks visible light. If Hubble had been underestimating the distances to its Cepheid calibrators because of dust contamination, then James Webb's infrared vision, which sees through dust, should give shorter distances and a smaller Hubble constant. The Cepheids would come into alignment with Planck. The crisis would dissolve. The opposite happened. James Webb's infrared measurements of the same Cepheids gave the same distances Hubble had been reporting. The dust correction had been right all along. There was no hidden bias. The April 2026 result tightened the screw one more turn. The distance network architecture combined three independent kinds of distance indicators, each of which could catch errors in the others. The Cepheids agreed with the red giant branch stars, which agreed with the carbon stars. All three pointed to the same answer: 73.5 kilometers per second per megaparsec, 1% precision. 5 sigma disagreement with Planck. That is where we are, a decade of hoping for the problem to dissolve. The problem did not dissolve. The problem got more precise, more confirmed, more impossible to wave away. And the Hubble tension is, as I said earlier, just the first of many fronts on which the standard model of cosmology is failing. The next one is about something even more fundamental than the expansion rate. It is about whether the universe itself is as smooth and well-behaved as the standard model assumes. Is less than break time equals 1s, is greater than number, part 3. What the sky refuses to confirm. Imagine the universe as an enormous batter of matter. Galaxies, dark matter, hot gas, cold gas, dust, everything. The batter is not uniform. There are lumps and clumps and threads of denser regions running through it. The pattern of those lumps was set very early in the universe's history by quantum fluctuations during a brief period of rapid expansion called inflation, and then amplified by gravity over billions of years. If you could see dark matter directly, the universe at large scales would look like a kind of cosmic web. Filaments of matter, hundreds of millions of light years long, intersect at dense knots that host the largest galaxy clusters. Between the filaments are immense voids, bubbles of near emptiness, some of them stretching across hundreds of millions of light years with almost no galaxies inside. The whole structure is sometimes called the large-scale structure of the universe, and it is one of the most beautiful predictions of the standard model. Computer simulations of the model, run on supercomputers, produce a cosmic web that looks indistinguishable from the one we observe in coarse features. The agreement at large scales is one of cosmology's quiet triumphs. The disagreement comes in the details. The standard model of cosmology makes a very specific prediction about how lumpy the universe should be. The prediction comes out of the cosmic microwave background, the same light source we use to predict the Hubble constant. From the pattern of hot and cold spots in the cosmic microwave background, you can calculate exactly how much matter should have clumped together by the time the universe was, say, 5 billion years old, or 10, or 13. The clumpiness parameter is conventionally called S8. It has a fancy mathematical definition involving standard deviations of mass fluctuations on 8 megaparsec scales, but the concept is straightforward. How lumpy is the universe? We can also measure the lumpiness directly. The most powerful technique is called weak gravitational lensing. Light from distant galaxies, on its way to our telescopes, has to pass through everything in front of it. The total matter along that path bends the light slightly, like ripples in a window pane. By statistically measuring the distortions in the shapes of millions of distant galaxies, you can map out the total matter distribution between us and them. This includes dark matter, which you cannot otherwise see. Several massive surveys have spent the last decade doing exactly this. The Kilo Degree Survey, abbreviated KIDES, working from telescopes in Chile and the Canary Islands. The Dark Energy Survey, abbreviated DES. The Hyper Suprime Cam Survey, on the Subaru telescope in Hawaii. Their results agree with each other and disagree with the cosmic microwave background prediction. The universe, as measured by weak lensing in the late universe, is less lumpy than the standard model predicted. The disagreement is currently around 2 to 3 sigma, not yet 5. Not yet at the level of the Hubble tension, but it is the same direction of disagreement. Late universe measurements are coming in lower than the early universe predictions. Think about what that means physically. Take the cosmic microwave background pattern, with its tiny temperature fluctuations of a few parts in 100,000. Those fluctuations are the seeds. They are the slightly denser and slightly less dense regions of the very early universe. Gravity should amplify those seeds over 13 billion years, building them up into galaxies and clusters and the cosmic web. The standard model contains a precise recipe for that amplification, and the recipe predicts a specific lumpiness today. We are measuring less lumpiness than the recipe predicts. Either the seeds were slightly different from what the cosmic microwave background says they were, or the amplification process is slightly different from what gravity in the standard model predicts, or something has been smoothing the universe out between the seeds and the present. None of these options is comfortable. If it were just the Hubble tension and the S8 tension, you could imagine some clever fix. A new ingredient that adjusts the expansion rate and the lumpiness in just the right ways to bring the late universe back into agreement with the early universe predictions. People are trying. There are dozens of papers proposing such fixes. None of them have been confirmed. But there is another piece of evidence, and it comes from the James Webb Space Telescope, looking in the opposite direction, not at the late universe, at the early universe, at galaxies that existed when the universe was less than 500 million years old. When James Webb's earliest survey images came back, the cosmology community was, briefly, ecstatic. The telescope was working better than expected. Then the analysis started, and the ecstasy curdled. Galaxies at redshifts of 7, 8, even 10, meaning we are looking back to when the universe was a small fraction of its current age, looked more developed than they had any right to be. Some of them appeared to have stellar masses that, in the standard model, would have required converting more than 80% of the available gas into stars in the first few 100 million years. Even 57% had been considered the rough theoretical ceiling. The mainstream response was reasonable. Maybe these galaxies are not as massive as they first appear. Maybe they are smaller than we think, and the light is being concentrated by some combination of bursty star formation episodes and active supermassive black holes adding extra brightness. Some of this has turned out to be true. As the analysis has matured, the masses of some of these early galaxies have been revised downward. The crisis has softened, but it has not gone away. There are still more massive galaxies in the early universe than the standard model predicts. The specific cases are worth naming. JADESGSZ 140 is currently the most distant confirmed galaxy, observed by James Webb at a redshift just above 14, meaning we see it as it was when the universe was only about 290 million years old. It is more luminous and apparently more developed than LCDM galaxy formation models comfortably allow at that epoch. Sears 93316, an earlier candidate, was thought briefly to break the record before its redshift was revised. The pattern is not that the universe contains one or two impossible galaxies. The pattern is that the universe at high redshift contains too many bright galaxies spread across too much of the sky for the standard formation timeline to absorb them all without strain. Star formation in the first 500 million years appears to have been more efficient than the model expected by a substantial factor. Astronomers have proposed cosmic dust populations, exotic initial conditions, and modified inflation scenarios to explain it. None has been confirmed. So now you have three independent fronts, each of which is showing a discrepancy with the standard model, and each of which is showing it in a way that is broadly consistent with the others. The universe is expanding faster in the present than the early universe predicts. The universe is less lumpy in the present than the early universe predicts. The early universe itself contains galaxies that are more developed than the standard model says it should. 3 different probes, 3 different time periods, 3 different physical systems, and all 3 are telling you that the connection between the early universe and the late universe is not the connection the standard model proposes. You can patch any one of these. You can patch any 2 of them with enough cleverness. Patching all 3 at once, without breaking everything else the model successfully predicts, is starting to look impossible. I want to dwell for a moment on the word independent, because it is doing a lot of work here. The Hubble tension is measured using local supernovae and Cepheid stars compared against a cosmic microwave background prediction. The S8 tension is measured using weak gravitational lensing of light from distant galaxies compared against the same cosmic microwave background prediction. The James Webb Galaxy Puzzle is measured using infrared spectra of high redshift sources compared against galaxy formation simulations rooted in the cosmic microwave background. The 3 measurements share one anchor, the cosmic microwave background, and the cosmic microwave background measurement is, by independent verification, extremely accurate. The pieces being compared against the cosmic microwave background are entirely independent of each other. Each one could be wrong on its own. The probability that all 3 are wrong in the same direction by accident is vanishingly small. Either the cosmic microwave background calibration is somehow biased in a way that has eluded 20 years of cross-checks, or the standard model that connects the cosmic microwave background to today is broken in a way that affects multiple measurements simultaneously. The second option is, increasingly, the consensus interpretation in the corridor conversations. And, as I am about to show you, dark energy itself, the most mysterious ingredient in the standard model, the one that makes up more of the universe than anything else, has started to behave in a way it was never supposed to behave. Is less than break time equals 1s is greater than number, part 4, the constant that isn't constant. On a mountain in southern Arizona called Kitt Peak, there is a telescope that does something no telescope before it has ever done. It has 5,000 robotic optical fibers at its focal plane, each one of which can be aimed independently at a different galaxy at the same time. In a single exposure, this telescope can capture the spectra of thousands of galaxies simultaneously. The telescope is called DESI, which stands for the Dark Energy Spectroscopic Instrument. Its job is to build the largest 3-dimensional map of the universe ever made. To understand why DESI matters for the story I am telling, you have to understand what dark energy is as a concept and how DESI tests it. Dark energy is the term we use for whatever is driving the accelerated expansion of the universe. We discovered it, accidentally, in 1998 by watching distant supernovae appear dimmer than they should. The simplest mathematical way to describe dark energy is to say that empty space itself has some constant energy density. Einstein had actually introduced a parameter for exactly this in his original equations of general relativity in 1917, before the expansion of the universe had been discovered. He used it to keep the universe static. When Hubble discovered the expansion in the 1920s, Einstein removed the constant and called it the biggest blunder of his life. Decades later, when dark energy was discovered, the constant came back. We call it the cosmological constant, written as the Greek letter lambda. The standard model of cosmology is literally called lambda cold dark matter, abbreviated LCDM. The lambda is dark energy. The defining feature of a cosmological constant is that it is constant, the same energy density everywhere in space, the same energy density at every time in the universe's history. Whatever dark energy is, in the standard model, it has the same strength now as it had 13 billion years ago. DESI's job is to test that assumption directly. By measuring the positions and recession velocities of tens of millions of galaxies across 11 billion years of cosmic history, DESI can map how fast the universe was expanding at every point along that history. If dark energy has been the same the whole time, the expansion history should match the prediction of a constant lambda. If dark energy has been changing, the expansion history will look different. The specific tool DESI uses is called baryon acoustic oscillations, sometimes shortened to BAO. Imagine the very early universe, in the first 400,000 years before the cosmic microwave background light was released. The cosmos was a hot plasma. Tiny overdensities of matter created pressure waves, actual sound waves that traveled outward at a measurable speed for hundreds of thousands of years before being frozen in place when the universe cooled enough to become transparent. Those frozen waves left a characteristic distance scale in the distribution of matter, about 500 million light-years across at present. Galaxies today are very slightly more likely to be found at that specific separation from each other than at any other separation. The pattern is faint. You can only see it statistically by counting pairs of galaxies across a survey of millions, but it works as a cosmic ruler. The same ruler, imprinted across the entire history of the universe by the same plasma physics, gives DESI a way to measure how the universe has stretched at every cosmic time with extraordinary precision. In March of 2025, DESI released its first major results. The data did not match the prediction of a constant lambda. The data preferred a model in which dark energy was stronger in the past and is weakening today. The signal strength in the DESI data alone was about 2.8 sigma. When the DESI data was combined with cosmic microwave background data from Planck and supernova data from the past few decades, the signal strength rose. Depending on which datasets you combined, the preference for evolving dark energy reached between 3 and 4.2 sigma. This is not yet a 5 sigma discovery. It is not yet the threshold at which the community would officially declare dark energy to be dynamic. But it is close, and the importance is enormous because of what dark energy is. The cosmological constant is a 2-letter parameter L that is supposed to be constant across all of space and time. It is supposed to be the simplest, most boring ingredient in the universe, a single number fixed forever. If it isn't, then the standard model of cosmology is wrong at its most fundamental level. I want to spend a moment on one technical detail, because it matters. The DESI team did something unusual in the way they ran their analysis. They blinded the result to themselves. They wrote the software, they ran the data, they did the corrections, all while a final transformation kept the actual numerical answer hidden from the people doing the work. Only at the very end of the analysis, when everything had been frozen, was the blind removed and the answer revealed. The reason is that cosmologists know themselves. The temptation to keep tweaking until the data agrees with the existing model is enormous and largely unconscious. Blinding the analysis removes that pressure. When the DESI team unblinded their first dataset and saw a signal for evolving dark energy, they had no way to have nudged the analysis toward that conclusion. They had been working in the dark, in the literal sense. The result is the result. The implications are unsettled, and the field is in genuine disagreement about what they are. The simplest possibility is something called quintessence, a hypothetical scalar field whose energy density changes over cosmic time. This idea has been around for decades, but it has always been considered a less elegant alternative to a true constant. If DESI is right, quintessence is suddenly back at the center of the conversation. A more exotic possibility is phantom dark energy, a scalar field with even stranger properties that would lead to a far future in which the expansion accelerates so rapidly that galaxies and eventually atoms themselves are torn apart, a scenario physicists call the Big Rip. Phantom dark energy violates a condition called the null energy condition that most physicists consider a kind of sanity check on physical fields, and so it makes everyone uncomfortable. The most radical possibility is that general relativity itself is wrong on cosmological scales. That what we have been interpreting as dark energy is not a substance or a field at all, but a sign that the equations of gravity behave differently at the scale of the entire observable universe than they do in the solar system. That last possibility deserves a small expansion, because it is the one most people have not heard. General relativity has been tested with extraordinary precision in regimes where the gravitational field is moderately strong orbits in the solar system, the bending of light by the sun, the time delays of signals passing near massive bodies, the inspiral and merger of binary neutron stars. The theory has passed every test in those regimes. What has never been tested, in any rigorous sense, is whether general relativity is the correct theory of gravity on scales of hundreds of millions or billions of light years. There is no laboratory at those scales. There are only observations of how matter moves at those scales, and the interpretation of those observations has always assumed general relativity is correct. If it is wrong on cosmological scales, every observation made at those scales has been reinterpreted through the wrong frame. Dark energy might be the simplest sign of that wrongness. Modified gravity theories have been around for a long time. They were treated with hostility for decades. They are now treated with cautious interest, because the alternative, adding two unknown ingredients, dark matter and dark energy, to general relativity in order to make it fit the data, is not exactly elegant either. What DZ has done is push the most uncomfortable possibility from the fringe to the center. Whatever dark energy is, it is probably not what we thought it was. The most fine-tuned number in physics is probably also not a number. It is probably a process. I want you to hold this realization alongside the Hubble tension and the S8 tension and the James Webb early galaxies. Each of these is a separate front of disagreement with the standard model of cosmology. Each one has its own statistical significance. Each one has its own potential resolutions. The story so far would already be remarkable if we stopped here. The model is failing in independent ways, and we are watching it happen in real time, in published results, in major journals, with no manufactured drama. But there is something even stranger about dark energy that has nothing to do with whether it is changing. The strangeness is the number itself, and the number itself is the worst prediction in the history of science. Is less than break time equals 1s is greater than number. Part 5. The worst prediction in the history of science. There is a phrase that appears in serious physics papers, and you can find it on the Wikipedia entry for the cosmological constant, and you can find it in Scientific American articles written by professional physicists. The phrase is the worst prediction in the history of science. It refers to a specific calculation that goes wrong in the most spectacular possible way. Here is the calculation. Quantum field theory, the framework underneath the standard model of particle physics, says that empty space is not empty. Every quantum field, and there are dozens of them, one for each kind of fundamental particle, has a non-zero energy even in its ground state. These zero-point energies are not optional. They are required by the mathematics of quantum mechanics in exactly the same way that the uncertainty principle is required. If you add up the zero-point energies of all the quantum fields in the universe, you get a vacuum energy density. You can calculate it. The calculation is not subtle. You take the energy of each mode of each field, you add them up, and you get a number. The number is enormous. The exact value depends on where you stop adding modes. If you stop at the Planck scale, the scale at which quantum gravity is expected to become important, you get a vacuum energy density that is 120 orders of magnitude larger than the value we actually observe. If you are more conservative and stop at scales where we still trust the calculation, you get something on the order of 60 orders of magnitude too large. There has been some technical work suggesting the most careful Lorentz invariant version of the calculation might bring this down to around 60 orders of magnitude rather than 120. The numbers shift depending on assumptions. The point is that no version of this calculation gives anything remotely close to the observed value. Let me try to make the size of this discrepancy visceral. 60 orders of magnitude. That is a 1 followed by 60 zeros. There are approximately 10 to the 80 atoms in the entire observable universe. If you wanted to write out the number representing the smaller version of this discrepancy, atom by atom, with 1 zero per atom, you would need a substantial fraction of all the atoms in existence. The larger version of the discrepancy, 1 followed by 120 zeros, exceeds the number of atoms in the universe by 40 orders of magnitude. You could not write the number using all the atoms in the universe as ink. The number is too big to be written by the matter that exists. This is not a small error. This is not we got the sign wrong, or we got the wrong constant by a factor of 2. This is the largest discrepancy between theoretical prediction and observation in any field of science, ever, by a margin so large that it is, in a literal sense, unwritable. The accepted explanation, if you can call it that, is that some unknown mechanism cancels the predicted vacuum energy, almost, but not quite perfectly. The almost leaves behind the tiny residue we observe as dark energy. The cancellation has to be exact to roughly 1 part in 10 to the 120. That is the level of fine-tuning the universe appears to have done in order to make the answer come out the way we see it. To put that fine-tuning in human terms, imagine balancing a pencil on its tip. A normal pencil, balanced on a normal table, with a normal nudge from the air, will fall over in a fraction of a second. To make the pencil stand up for the age of the universe, you would need an unimaginably precise initial placement. The fine-tuning we are asking the cosmological constant to perform is, in proportional terms, far more precise than even that. It is a balance maintained across roughly 120 orders of magnitude of cancellation. No physical mechanism we know about would naturally produce such precision. And yet, here we are, in a universe where the cancellation has occurred. A physicist, looking at this from the outside, who had never been trained in the cultural acceptance of the cosmological constant problem, would say one of two things. They would say that the calculation must be wrong, because no physical theory should be that far off. Or they would say that the universe is fine-tuned to a degree that requires an explanation, because no physical universe should be a residue of a near-perfect cancellation that nobody can explain. Steven Weinberg, one of the architects of the Standard Model and a Nobel laureate, wrote in 1989 what is still the best survey of the cosmological constant problem. He laid out the calculation, walked through the size of the discrepancy, considered every proposed solution that had been published up to that point, and concluded that none of them worked. Weinberg's paper remains, more than 35 years later, almost untouched in its essential message. There is no accepted physical mechanism for cancelling the vacuum energy to 1 part in 10 to the 120. Every proposal either does too much cancellation or too little. The most promising approaches involve symmetries we cannot find or environments we cannot test. The problem has not been solved. It has been quietly stepped around. The mainstream response, when pressed, is increasingly to invoke the anthropic principle. Maybe the cosmological constant is 1 part in 10 to the 120 of its naive prediction, because only universes where the cancellation happens to leave a small residue can host observers. In universes where the residue is larger, the universe expands so fast that galaxies never form. No galaxies, no stars, no planets, no observers. We are here because we are in one of the very rare universes where the cancellation worked out. This explanation requires the existence of many other universes and multiverse. It also requires us to accept that physics is no longer a search for principles that explain why the constants are what they are. Physics, on this view, becomes a kind of statistical lottery. You stop asking why the cosmological constant is what it is. You start asking what fraction of universes in the multiverse have observers, and you note that observers necessarily find themselves in such universes. Many physicists hate this. They hate it because it is unfalsifiable. They hate it because it concedes the original question. They hate it because it suggests that physics has hit a wall it cannot get past. They hate it because they did not become physicists to study lotteries. Weinberg himself, late in his career, came partway around to the anthropic argument. In 2006, he co-wrote a paper that took the anthropic prediction of the cosmological constant seriously and concluded that the observed value was, in fact, roughly what an anthropic calculation would predict a residue close to the upper limit of what observers could tolerate. That came as a surprise to a generation of theorists who had thought the explanation had to be principled rather than statistical. The shift was significant. When one of the people who built the Standard Model concedes that the worst prediction in physics might be answered by selection effects rather than dynamics, you are watching the field move. And now, Desi is telling us that this number, this exquisitely fine-tuned residue that we somehow got right, is probably not even constant. The most fine-tuned number in physics may also be changing over time. The cancellation, whatever it is not perfect, not just in space, but also in cosmic history. The mystery is now even harder than it was a year ago. The realization that should land on you here is this. The Standard Model of cosmology contains a parameter that, even by its own framework, is the most embarrassingly wrong prediction in the history of physics. And the parameter is now telling us that even our wrong prediction was incomplete because the parameter itself appears to be evolving. We do not understand dark energy. We do not understand dark energy so completely that the depth of our not understanding has now grown a second floor. And I have not even mentioned what is happening to the constants of physics themselves. Is less than break time equals 1s? Is greater than number. Part 6. What if time itself is drifting? There is one more crack in the standard picture that I want to walk you through before we leave cosmology and turn to particle physics. It is the strangest of the cracks, because it is not about the contents of the universe. It is about the rules. Physics is built on the idea that the constants are constant. The speed of light in a vacuum is the same in every laboratory, in every galaxy, in every era of the universe. The fine structure constant, which determines the strength of the electromagnetic force, is the same in the center of the Sun as it is in the early universe. The ratio of the proton mass to the electron mass is fixed for all time. These assumptions are not just convenient, they are the bedrock on which most of physics rests. If the constants are different in different places or at different times, then almost every astrophysical observation has to be reinterpreted, and most of the calculations we use to deduce conditions in the early universe become unreliable. For the most part, this assumption has held up under enormous scrutiny. Tests of the constancy of the fine structure constant on Earth, comparing atomic clocks of different types over many years, find no change to 1 part in 10 to the 17 per year. Tests using astronomical data, comparing absorption spectra of quasars at large redshifts to laboratory measurements, have found tentative hints of differences at the level of a few parts per million. The hints are not consistent. Different teams analyzing different quasar populations have reached opposite conclusions. The mainstream verdict is that the constants are probably constant, and the apparent variations are systematic effects we have not yet pinned down. But notice the structure of the conversation. The fact that the question is being asked seriously in major journals is itself a sign of how much the field has shifted. 20 years ago, suggesting that the fine structure constant might be varying was treated as a fringe position. Now, it is a working research program with its own measurements, its own debates, its own conferences. If even one of these tentative measurements turns out to be real, the consequences are large. If the constants of physics are varying, even slightly, then the laws of physics are not the same at all times. Cosmological evolution involves not just the contents of the universe matter, dark energy, but the rules themselves. The whole framework on which standard model predictions are built assumes a fixed background of constants. If the background is varying, the predictions need recalibration. The fine structure constant deserves a word of its own. It is conventionally called alpha, the Greek letter alpha. Its value is approximately 1/137, which is a number physicists find suspiciously close to a clean integer ratio and have spent the better part of a century trying to derive from first principles. Nobody has succeeded. Alpha controls how strongly electrons bind to nuclei, which controls the chemistry of every atom, which controls the chemistry of every molecule, which controls the chemistry of every biological system. A change in alpha by a few percent would unmake life. A change by a few parts per million across cosmic history would still be a profound shift in the rules. The fact that we cannot definitively rule out such a change tells you how thin the floor of constancy actually is under our feet. I want to mention, gently, that this is not the only place where the constancy of fundamental physics has been questioned. There are theoretical proposals, Roger Penrose's conformal cyclic cosmology, for one in which the universe undergoes repeated cycles, with the constants and the contents resetting in some sense between cycles. There are bouncing cosmologies, proposed by Paul Steinhardt and Neil Turok, among others, in which the Big Bang was not the beginning, but a phase in an oscillating sequence. Each of these proposes that our universe is not the only universe, and not even the only era of this universe. Each of them is mainstream enough to appear in peer-reviewed physics literature. Each of them is also speculative enough that no specific prediction has yet been confirmed. Penrose's conformal cyclic cosmology has a particularly strange detail. Penrose argues that in the very far future, after all matter has decayed and all black holes have evaporated, the universe will consist of nothing but massless particles, photons and gravitons travelling at light speed. Without anything massive to provide a sense of scale, time itself ceases to have meaning. The end of the universe, in this picture, becomes mathematically indistinguishable from the beginning of a new one. The Big Bang of our universe might have been the heat death of an earlier universe, smoothly continued. This is, to put it mildly, an extraordinary claim. It is also a peer-reviewed claim made by a Nobel laureate, taken seriously by enough cosmologists that experiments have been proposed to look for signatures of pre-Big Bang events in the cosmic microwave background. The reason I want you to hold these ideas in your mind, even briefly, is that they have a common feature with the Hubble tension and the Deci dark energy evolution. They all suggest that the universe might be a process rather than a state, that the laws and constants we have measured are not eternal features, but stages of something larger, that what we are seeing when we look at cosmic history is not a fixed model with varying contents, but a varying model with varying contents. The deepest version of the broken model story is not that one ingredient of the standard model is wrong. The deepest version is that the assumption of a single fixed framework describing the entire history of the universe might be the part that is wrong. That is enough speculation for the moment, and I want to be careful not to oversell. The constants of physics are, by every well-controlled laboratory measurement, constant. The cyclic and bouncing cosmologies are interesting and unconfirmed. What I want you to take from this is not a specific belief about what is happening. I want you to take an attitude, a willingness to hold open the question of whether the universe runs on fixed rules at all. There is something restful about acknowledging this kind of openness. Most of human history has happened under the implicit assumption that the rules of nature, whatever they were settled and merely waiting to be uncovered. The job of the scientist was to read them off, like translating a foreign text. Our generation may turn out to be the first to seriously consider that the text might be writing itself as we read it, that the universe might not have been designed to be intelligible at the level we have been trying to understand it. That intelligibility might be a local feature, true within certain regimes, and the larger structure might require entirely different ways of thinking. None of this is settled. Most of it is speculation. The fact that the speculation is happening among professional physicists is what is new, and now I have to turn from cosmology to the other half of the story. Because everything I have described so far is about the model of the universe at large. There is another standard model, the one that describes particles and forces. It has been the most successful framework in physics for 50 years. It is also failing in known and unfixable ways. And the failures over on the particle physics side and the failures over on the cosmology side are pointing at each other. Is less than break time equals 1s. Is greater than Part 7. 40 years of not finding dark matter. The standard model of particle physics, often called the standard model with capital letters to distinguish it from cosmology, is a catalogue of all the known fundamental particles and 3 of the 4 known forces. There are quarks, which make up protons and neutrons. There are leptons, which include electrons and neutrinos. There are gauge bosons, which carry forces. There is the Higgs boson, which gives mass to certain particles. The catalogue has been tested in particle colliders for half a century to a precision that, in some cases, reaches 1 part in a trillion. The standard model is, by every reasonable measure, the most successful scientific theory ever written. It is also incomplete. The standard model does not include gravity. It does not include dark matter. It does not include dark energy. It does not explain why the Higgs mass is what it is, or why neutrinos have any mass at all, or why there is matter in the universe instead of equal parts matter and antimatter. The standard model is, in other words, a description of about 5% of the contents of the universe, with profound silences on the rest. Dark matter is the most pressing of those silences. The gravitational evidence for dark matter is overwhelming and has been for decades. Galaxy rotation curves are wrong if you only count the visible matter. Galaxy clusters move in ways that require more mass than we can see. The cosmic microwave background structure cannot be reproduced without some kind of matter that doesn't interact with light. The bullet cluster, a collision between 2 galaxy clusters observed in 2006, showed the gravitational mass and the visible mass separating from each other in a way that requires an invisible component. There is something out there. It is roughly 5 times more abundant than ordinary matter. We have known this since the 1970s and confirmed it dozens of ways since. The historical credit for dark matter usually goes to Fritz Zwicky, a Swiss astronomer who in 1933 observed that the galaxies in the Coma cluster were moving too fast to be held together by the visible matter and posited the existence of unseen matter to explain the discrepancy. The credit also goes to Vera Rubin, an American astronomer who in the 1970s showed that the rotation curves of spiral galaxies, the speed at which stars orbit their galactic centers as a function of distance, did not slow down with distance the way they should. Stars on the outskirts of galaxies are moving roughly as fast as stars near the centers. This pattern is impossible unless there is an enormous halo of invisible matter wrapping around each galaxy, holding the outer stars in place gravitationally. Rubin's measurements were so clean and so consistent across so many galaxies that by the 1980s, the gravitational case for dark matter was effectively closed. What remained, and remains, is figuring out what it is. What we do not know is what dark matter is made of. The leading candidate, for decades, was the WIMP, the weakly interacting massive particle. The reasoning was elegant. If you assume a new particle with a mass somewhere around that of a heavy atomic nucleus, and interactions roughly as weak as the weak nuclear force, you naturally get a particle that would have decoupled from the rest of the universe in the early Big Bang and survived in roughly the abundance dark matter requires. This is called the WIMP miracle. Physicists love a miracle that comes for free. Theoretical predictions of WIMP properties were specific enough that we could build experiments to look for them directly. The strategy was to put a clean detector underground, far enough below the surface that ordinary radiation gets filtered out by the rock, and then wait for one of the trillions of dark matter particles passing through the Earth every second to bump into a nucleus in the detector. The interaction would be extraordinarily rare. The detector would have to be exquisitely sensitive. The signal would be a tiny flash of light or a tiny electrical pulse from a single nuclear recoil. A series of these experiments has been built over the past 4 decades, each one more sensitive than the last. The flagship right now is Lux Zeppelin, abbreviated LZ, located in the Sanford Underground Research Facility in South Dakota. The detector sits about a mile below ground in a former gold mine. It contains almost 10 metric tons of liquid xenon, cooled to about 180 degrees below zero on the Celsius scale. The xenon is kept inside a series of nested containers, each one shielding against background radiation from the next layer outward. The result is the cleanest, most sensitive dark matter detector ever built. The level of cleanliness required is something most people have never had to think about, so it is worth describing. The xenon used in LZ is screened for radioactive contaminants down to parts per billion of parts per billion. Every component of the detector, the steel, the wires, the electronics, the seals is screened in an underground low background laboratory for trace amounts of uranium and thorium that would otherwise produce background events indistinguishable from a dark matter signal. The construction took years just to source materials that met the specifications. The result is a detector in which a single radioactive decay anywhere inside it would dominate the background rate. The team built an environment in which the only events should be the ones they are looking for. In 417 days of running, no events of the right kind appeared. In December of 2025, the LZ collaboration released results from 417 live days of data taken between March of 2023 and April of 2025. The dataset is the largest ever collected by a dark matter detector. The result? No signal. No WIMPs detected. The new limits on WIMP interactions are the most stringent ever published. A similar experiment in Italy, called Xenont, has reported similar results. Both experiments are now sensitive enough that they are starting to detect neutrinos from the Sun bumping into their xenon nuclei. This is, in some ways, a triumph. Solar neutrinos had never been detected this way before. It is also, in another way, a wall. As the experiments grow more sensitive, the solar neutrinos themselves become a kind of irreducible background called the neutrino fog. Below the neutrino fog, you can no longer easily distinguish a dark matter signal from a neutrino interaction. We are approaching the floor of conventional WIMP searches. What this means in plain language: 40 years of dark matter direct detection, hundreds of millions of dollars. The cleanest laboratory experiments humans have ever built, located in the cleanest underground laboratories ever excavated. Result: the WIMP, in the form predicted by the theories that motivated the search, does not exist in the parameter space we have been searching. The community's response has been a quiet pivot. New candidates are being proposed. Axions extremely light bosons, originally proposed to solve a different problem in particle physics, called the strong CP problem. Several experiments, including ADMX and Haystack, are targeting them. Sterile neutrinos, a hypothetical fourth neutrino species that doesn't participate in the weak force. Primordial black holes, small black holes formed in the first fractions of a second after the Big Bang. Ultralight dark matter, in which the dark matter particle is so light that it behaves more like a classical field than like a particle. Self-interacting dark matter, in which dark matter particles can scatter off each other in addition to interacting gravitationally. Each of these candidates would require completely different detection strategies. Axion experiments use sensitive microwave cavities in strong magnetic fields to listen for the conversion of axions into photons. Primordial black hole searches look for gravitational microlensing signatures as the black holes pass in front of background stars. Sterile neutrino searches look at neutrino oscillation experiments for anomalies in flavor mixing. Ultralight dark matter searches use atomic clocks to look for oscillations in the values of fundamental constants. The variety of approaches is enormous. The point is that nobody knows where to look anymore, and so the field is looking everywhere it can imagine. Each of these is a serious research program. None of them has been confirmed. The field is fragmenting. 40 years ago, the dominant idea for what makes up most of the universe's matter was one specific thing, the WIMP. Today, the dominant idea is, we have no idea, and here are 6 different things it could be, all of them speculative. This is not a small failure of the standard model. Dark matter is 5 times more abundant than ordinary matter. The model that catalogues the contents of the universe does not contain its most common form of matter. And the framework we use to motivate the search for that matter, in the form of the WIMP, has been mostly excluded by the experiments we built to find it. We are starting over. We do not know where to look. And before I move on, I should mention that dark matter wasn't the only thing the Large Hadron Collider was supposed to find. There was another theoretical framework, with deeper roots in the field's culture, that was supposed to crown the standard model and reveal the next layer of physics. That framework has had a quieter funeral than the WIMP, but it is just as dead, and the implications cut to the foundations of what particle physics has been doing for 50 years. Is less than break time equals 1s is greater than number part 8, the silent funeral of supersymmetry. For about 40 years, the most popular extension of the standard model was a framework called Supersymmetry, almost always abbreviated SUSY. The basic idea is elegant. Every particle in the standard model, every quark, every lepton, every gauge boson, the Higgs has a heavier supersymmetric partner. The partners are called sparticles, or more specifically, you have squarks and sleptons and gauginos and the Higgsino. The framework requires roughly doubling the number of fundamental particles, but in return, it pays for itself in elegance. There is an old joke in particle physics that supersymmetry is the most beautiful theory that has ever failed to be observed. The beauty is real, the failure also. To understand why the failure cuts so much, you have to understand how completely the field had committed to it. Roughly 1/3 of all theoretical particle physics papers between 1990 and 2010 involved supersymmetry in some way. The textbooks for graduate students had whole chapters dedicated to it. Conferences had entire sessions devoted to its phenomenology. Whole subfields existed only to work out what supersymmetric particles would do in different experimental signatures. When the LHC turned on in 2008, the dominant expectation was that the first major discovery would be a sparticle. A whole generation had been trained to recognize the experimental fingerprints of supersymmetric signatures. They were ready. The signatures did not appear. 3 things made supersymmetry irresistible to theorists. First, it solved the hierarchy problem. The Higgs mass, as measured at the Large Hadron Collider, is about 125 giga-electron-volts. Quantum corrections from interactions with virtual particles, especially the top quark, should drag the Higgs mass up to the Planck scale, which is about 10 to the 19 giga-electron-volts. The natural Higgs mass is roughly 16 orders of magnitude heavier than what we measure. To get the small Higgs mass we observe, you need a fine-tuning of 1 part in 10 to the 32. That is the hierarchy problem, and supersymmetry solved it by adding a heavy partner for every standard model particle with cancellations between the contributions that naturally keep the Higgs mass small. Second, supersymmetry naturally produced a dark matter candidate. The lightest supersymmetric particle, in most versions of the theory, is stable, neutral, and weakly interacting. It is, in other words, exactly the WIMP we just talked about. Supersymmetry provided the theoretical motivation for an entire generation of dark matter searches. Third, supersymmetry made the 3 forces of the standard model unify cleanly at high energies. The electromagnetic, weak, and strong forces have different strengths at low energies, but their strengths change with energy, and in the standard model they almost but not quite converge at very high energies. With supersymmetry, they converge exactly. This kind of unification is a signpost theorists love because it suggests the 3 forces are different faces of a single underlying theory. The Large Hadron Collider, the 27-kilometer ring of superconducting magnets buried under the French-Swiss border at CERN, was constructed in significant part with the expectation that it would find supersymmetric particles below 1 tera-electron-volt in energy. If you had asked theorists in 2008 to bet on what the LHC would find, the answer would have been supersymmetry first, then the Higgs. The LHC did find the Higgs in 2012 exactly as predicted, and then it found nothing, no squarks, no gluinos, no sleptons, no charginos, no neutralinos at the masses theorists had predicted. The exclusion limits have tightened year after year. Gluinos, the supersymmetric partners of the gluons, have now been excluded up to masses of about 2 tera-electron-volts. Other particles have similar limits. The most popular supersymmetric models, including the constrained minimal supersymmetric standard model that dominated the field's theoretical work for 2 decades, are gone. What the field has done in response is not declare supersymmetry dead. The official response has been to say that the parameter space has expanded, that non-minimal models are still viable, that some supersymmetric models naturally predict heavier particles. Every time the LHC excludes a region, predictions move just above it. The pattern is suspicious. It is the pattern of a theory that is being defended rather than tested. Some honest accounts from within the field have appeared. The physicist Sabine Hossenfelder, in her book Lost in Math, published in 2018, walked through interviews with theorists who had built their careers on supersymmetry and other naturalness-driven extensions. The common thread in those interviews was an unwillingness to admit, in public, that the framework had failed. In private, many of those same theorists conceded that they did not know what to do next. Hossenfelder's book was uncomfortable for the field because it made the corridor conversation public. Some physicists dismissed it as a journalistic exaggeration. Others quietly admitted she had heard them correctly. What has not gone away is the hierarchy problem that supersymmetry was supposed to solve. The Higgs mass is still small. The naturalness problem is still there. The standard model still requires a fine-tuning of roughly 1 part in 10 to the 32 to produce the Higgs mass we observe, and the framework that promised to explain this has not appeared in the experiments designed to find it. The naturalness doctrine, the idea that physical parameters should not require absurd fine-tuning to come out as observed, has been one of the field's guiding principles for 50 years. It has guided theorists, it has guided experimentalists, it has guided funding decisions about which experiments to build. The cosmological constant has been a problem for naturalness for a long time, with its discrepancy of 60 to 120 orders of magnitude. The Higgs mass was supposed to be where naturalness worked out, where the LHC would find the new physics that kept the small mass natural. The LHC did not find that physics. Naturalness, as a guiding principle, is failing on 2 fronts at once. The slow consequence of this failure is something the field is only beginning to absorb. If naturalness is not a reliable guide, then physicists have lost one of their main tools for deciding which theoretical directions to pursue. For 5 decades, the question, "Is this theory natural?" was a useful filter. Theories that required outlandish fine-tuning were demoted. Theories that explained their parameters as consequences of symmetries were elevated. Without that filter, the field is, in a real sense, navigating in fog. The questions that drove a generation of theoretical work have lost their force. New questions have not yet replaced them. If you tie this back to what we have been discussing on the cosmology side, the parallel is hard to miss. Both the standard model of cosmology and the standard model of particle physics are showing the same kind of failure. They both predicted that the next layer of physics would appear at a specific place for cosmology, in agreement between the cosmic microwave background and local measurements. For particle physics, in supersymmetric particles at the LHC, in both cases, the predicted place is empty. Both fields are now in the same uncomfortable position. Their best theoretical guesses for what comes next have not arrived, and in both fields, the absence is being filled by quiet adjustments to models that nobody quite wants to declare dead. The cosmologists keep stretching the standard model with new ingredients. The particle physicists keep raising the predicted masses of supersymmetric particles. Both are buying time. Both are running out of it. Is less than break time equals 1s, is greater than number, part 9, the tail that wagged the dog. I want to spend some time on 2 recent anomalies that went the other way. 2 cases where the data initially looked like it was breaking the standard model and the field got excited, and then the closer look brought the anomaly back into line. These stories matter because they shape how the field talks about anomalies in general, and because they show, by contrast, how serious the cosmological tensions actually are. The first story is about a particle called the muon. The muon is a heavy, unstable cousin of the electron. It has the same electric charge as the electron, but about 200 times more mass. Because of its mass, it experiences gravity and other interactions slightly differently. One of its measurable properties is its magnetic moment, the strength of its tiny intrinsic magnetism. The magnetic moment of any charged particle can be calculated with great precision in the standard model. For the muon, the standard model predicts a specific value, and any deviation from that value would be a hint of new physics virtual particles unknown to the standard model, contributing to the muon's magnetism in ways the theory does not account for. In the early 2000s, an experiment at Brookhaven National Laboratory measured the muon's magnetic moment and got a value that disagreed with the standard model prediction at about 3 sigma. Not enough to call a discovery, but enough to make people sit up. A follow-up experiment was built at Fermilab, with the goal of pinning the measurement down to a precision that would either confirm new physics or rule it out. The reason muons are useful for this kind of test, rather than electrons, comes down to the way virtual particles contribute to the magnetic moment. Heavy particles couple more strongly to heavier leptons. If there are new particles beyond the standard model particles too heavy to produce directly at the LHC, they would still show up indirectly in precision measurements of the muon, but only weakly in electrons. The muon is, in this sense, a probe for new physics at energies that no collider has reached. Every percentage point of precision improvement in the measurement is a percentage point further into the unexplored territory beyond the standard model. That is why the Fermilab experiment mattered. That is why the field cared so much about its result. The Fermilab Muon G2 experiment began publishing results in 2021, and over the following years, the disagreement with the standard model prediction grew, reaching about 4.2 sigma at one point. The field was, for several years, on the edge of declaring this the first discovery of physics beyond the standard model. Theorists wrote papers proposing what new particles might be responsible. In June of 2025, the Fermilab experiment released its final result, based on the entire run of data. The measured value of the muon's magnetic anomaly is now known to 127 parts per billion, which is exceptional precision. The experimental side of the story is solid. The detector itself is worth describing for a moment, because it is one of the most beautifully strange objects in modern physics. A storage ring, almost 50 feet across, originally built at Brookhaven in the 1990s, was transported by truck and barge across the eastern United States to Fermilab in 2013, intact and one piece, because disassembling it would have destroyed it. Inside the ring, muons travel in tight circles at near light speed, their magnetic spins wobbling in the ambient magnetic field. The wobble frequency is what the experiment measures, and the wobble frequency is what carries the information about the muon's magnetic moment. The theoretical side is what changed. The standard model prediction depends on a contribution from what are called hadronic vacuum polarization effects, which are notoriously difficult to calculate. For years, the calculations used a method called ratio, which gave a specific value that disagreed with the Fermilab experiment. But there is another method called lattice quantum chromodynamics, which uses massive supercomputer calculations to compute the same quantity from first principles. The lattice calculations had been giving slightly different answers from the ratio method, and over the past few years, the lattice calculations have improved and converged. In April of 2026, a new calculation was published in Nature that brought the standard model prediction into 0.5 sigma agreement with the experimental measurement. The anomaly is gone, the standard model held. There is no new physics in the muon's magnetic moment. The second story is about the W boson. The W boson is one of the carriers of the weak nuclear force, the force responsible for radioactive decay. Its mass is one of the parameters of the standard model, and it had been measured many times over the past few decades, with results consistent with the prediction. In 2022, the CDF experiment at Fermilab released a new measurement of the W boson mass, with claimed precision that exceeded all previous measurements combined. The value was 80.434 giga-electron-volts, which was roughly 7 sigma above the standard model prediction of 80.357. This was, briefly, the biggest tension in particle physics, the kind of tension that could justify a Nobel Prize. Theorists wrote papers within days, proposing extensions to the standard model that could accommodate the heavier W boson. The follow-up came from the LHC's CMS and ATLAS experiments. CMS published a new measurement in 2024 with the LHC's largest dataset. ATLAS published its own refined analysis. Both came out consistent with the standard model. The CDF result now looks like an outlier, a measurement that probably has a systematic bias the original team did not catch. The W boson mass anomaly is, like the muons, gone. I want to add one observation about how these resolutions felt to the people involved. In the months after the CDF result came out in 2022, theorists wrote roughly 200 papers, proposing new physics explanations for the anomaly. 200 papers written in a few months by professional physicists on the assumption that the measurement was correct. When CMS and ATLAS later showed the measurement was probably wrong, those 200 papers became, almost overnight, a kind of cautionary tale. They were not retracted. They were simply quietly stopped being cited. The pattern matters. The field is fast to propose new physics when an anomaly appears, and equally fast to forget those proposals when the anomaly disappears. The new physics ecosystem is partly opportunistic in this way. It responds to data. It does not predict data. The cosmological tensions, by contrast, have generated their own equivalent of those 200 papers, and the tensions have not gone away. The proposals are accumulating. I tell you these two stories because they are what the field hopes will happen with every anomaly. Better measurements, more careful theoretical calculations, a slow return to agreement with the standard model. This is what success looks like in particle physics. The standard model is so accurate that when something appears to deviate from it, the most likely explanation is that something was wrong with the measurement or the calculation, not with the model. This pattern has held for decades. The neutral kaon system in the 1960s, the W and Z bosons in the 1980s, the top quark in the 1990s, the Higgs in 2012, every prediction the standard model has made has been confirmed within experimental precision, and every apparent deviation has, eventually, either been reduced to a fluke or absorbed into the model through a refinement of calculations. The track record is unprecedented. No other theory in the history of science has stood up to this much testing this well. That is why the muon and the W boson stories ended the way they did. The model is genuinely that accurate. The model is also genuinely incomplete in known ways. Both things are true at once, and the asymmetry between cosmology and particle physics has to do with which kind of failure each field has been running into. And this is where the cosmological tensions look, by contrast, so serious. The Hubble tension started small. It has grown larger and more precise with every new measurement. The Deci signal of evolving dark energy started small. It has grown stronger as the data has accumulated. The S8 tension has held steady. The James Webb early galaxy results have been partly walked back, but not enough to disappear. The pattern in cosmology is the opposite of the pattern in particle physics. The standard model walks tensions back. The standard model of cosmology amplifies them. The narrative implication is unsettling. It is not that any one cosmological tension is unmistakably real. It is that the cumulative pattern, with multiple independent tensions all pointing in the same direction and growing rather than shrinking, looks different from the pattern that has historically resolved itself. We are running out of safe places for these anomalies to land. So, what do the physicists doing this work think? Privately, what do they say? That is the question I want to come to next, because the disconnect between what is said in private and what is said in public is the second half of the title, and the answer is more interesting than a conspiracy. Is less than break time equals 1s is greater than number, part 10. Why physicists won't tell you. The title of this video says that physicists refuse to talk about this. That phrasing is too strong, and I want to soften it carefully, because the truth is more interesting than a conspiracy. There is no conspiracy. There is a structural quiet, and it has identifiable mechanisms that have nothing to do with anybody hiding anything. The first mechanism is career risk. A physicist who declares the standard model of cosmology dead without proposing a complete replacement is taking a real and serious career risk. Tenure committees, grant review panels, journal editors all favor the cautious. Anomalies that fit the model are publishable. Anomalies that break it are publishable only if you can also propose how to fix them. A paper that says, "This looks like a serious problem, and I have no idea what causes it," is much harder to publish than a paper that says, "This looks like a serious problem, and here is a specific new physics model that could explain it." The system rewards constructive proposals over honest descriptions of failure. The second mechanism is funding. Major facilities, DESI, the Vera Rubin Observatory, due to begin operations soon, the Square Kilometre Array, the Euclid Space Telescope, eventually CMB, S4, are built on multi-decade timelines and funded by agencies whose budgets depend on selling Congress and parliaments a coherent narrative. The standard model is broken and we have no idea what comes next is not a fundable narrative. We are testing the standard model with unprecedented precision, and probing the edges of new physics is. Funding agencies do not directly suppress crisis language papers. They simply prefer to fund people who frame their work in a forward-looking, model-extending way. Over time, this preference shapes the language of the field. The third mechanism is publication bias. Journals are more receptive to papers that resolve tensions than to papers that confirm them. A reanalysis that shrinks the Hubble tension by including some new systematic effect is publishable. The same reanalysis that strengthens it can take twice as long to get through review because reviewers find more to criticize. This is partly human and partly structural. The combination is that the literature looks calmer than the field actually is. The fourth mechanism is the most subtle. The experts who would have to declare the standard model dead are the same experts whose careers, reputations, and life's work assume it is alive. This is not corruption. It is the human nature of expertise. You spend 40 years developing an intimate understanding of a framework, and when the framework starts to fail, your first instinct is to look for ways to fix it, not to declare it dead. The fixing is honest work. It is what science is supposed to do. But after enough fixes accumulate, the framework starts to look like the geocentric model with its dozens of epicycles, and someone, eventually, has to be willing to say so. The people best positioned to say so are the people least psychologically able to say so. What you get from these four mechanisms together is not silence. It is calibrated speech. At a press conference for DESI's 2025 results, the lead investigators said there were tantalizing hints that dark energy might be evolving. At the same conference, in private corridors between sessions, you could hear cosmologists describing the result as the most exciting thing in cosmology in 20 years. Both statements are true. They are aimed at different audiences. The press statement is calibrated for the public, where overclaiming has costs. The corridor statement is calibrated for peers, where understatement signals scientific maturity. There is a fifth mechanism worth naming separately, because it is the most subtle and the most pervasive. Call it the linguistic stickiness of the existing model. When you have spent a generation calling something the standard model, the word standard carries a quiet authority that no upstart framework can match. Calling LCDM the standard model means that any deviation from it has to be called a deviation, an extension, a modification. The default frame is preserved by the language itself. A young physicist who wanted to propose a fundamentally different framework would, by linguistic gravity alone, have to position their work as a deviation from the standard. This is a small thing. It is also, across decades, an enormous thing. The model becomes self-perpetuating not by force, but by vocabulary. A journalist sitting in the press conference picks up the press statement. The journalist writes a piece for a major newspaper saying that DESI has found intriguing hints that dark energy might be changing. The article is technically accurate. It does not convey the level of internal excitement, because the internal excitement was not on display at the press conference. The article reaches 1 million readers, none of whom understand that the field is, behind the scenes, in a state of barely contained agitation. The miscommunication is not anybody's fault in particular. It is a structural translation problem. The press conference uses one register of speech. The peer-reviewed paper uses another. The corridor conversation uses a third. The hierarchies of language carry hierarchies of confidence, and the public version is, by design, the most conservative version. None of this is wrong. It is, however, the reason the average viewer has heard far less about the current state of cosmology than the average cosmologist has been thinking about it. This is not a moral failure. It is what happens when a paradigm is dying and the next one has not been born. There is a useful word for this state of affairs that comes from the philosopher Thomas Kuhn. He called it normal science under pressure. In ordinary times, science proceeds by puzzle solving within an accepted framework. When the framework starts to fail, normal science continues, but the puzzles get stranger and the proposed solutions get more baroque. The framework is patched and repatched. The community defends the framework because the alternative is paralysis. Eventually, in some cases, the patches accumulate to the point where a younger generation declares the whole edifice broken and starts over. That is a scientific revolution. We are, right now, in the patched stage. Whether we are heading for a revolution or for a quiet resolution that brings the model back into agreement with the data, nobody knows. Both have happened before. Every great moment in physics has looked like this from the inside. Consider the late 1800s. Lord Kelvin, in 1899, gave a famous lecture in which he said that the future of physics looked like a clear sky with only 2 small clouds, remaining the Michelson-Morley experiment, which would shortly lead to relativity, and the blackbody radiation problem, which would shortly lead to quantum mechanics. Kelvin's 2 clouds were the entire foundation of 20th century physics. He did not know that. He was 80 years old, the most respected physicist in the world, and he thought the work was almost done. The corridor talk in 1898, if you could have heard it, was probably terrified. The press releases were probably calm. This is the moment we are in now. Calm press releases. Terrified corridors. The model is breaking, the physicists know, and the silence is not suppression. It is the silence of people who do not yet know what to say. They are saying tension because tension is fundable and crisis is not. They are saying intriguing hints because intriguing hints can be reported by journalists without misquoting the field. They are saying we need more data because in fact they do need more data and they need it before they can say anything more concrete. None of this is wrong. None of this is dishonest. It is the texture of a paradigm shift in progress, viewed from inside the paradigm by people who do not yet know which way the shift is going. What does the shift look like if you let yourself imagine it? That is the next question, and the candidates for what comes next include some ideas that were considered fringe 20 years ago, but are now openly discussed at the highest levels of the field. The fringe is not what it used to be. Is less than break time equals 1s. Is greater than number, part 11. The fringe that wasn't fringe. When a paradigm is dying, and the next one has not been born, the fringes get a quiet promotion. Ideas that were unrespectable a generation ago are now openly discussed in faculty seminars at top universities. Some of these ideas will turn out to be right. Most of them probably won't. The point is not that any specific fringe idea is correct. The point is that they are now considered legitimate working hypotheses, and the fact that the field is open to them at all is itself the news. One way to read the rise of the fringe is as a sign that the field is exhausted with the conventional. Another way to read it is as healthy intellectual humility, the recognition that we do not know what we do not know, and that conservatism about possibilities is not the same as conservatism about evidence. Both readings are partly true. The anthropic principle is the cleanest example. The idea is that the cosmological constant is finely tuned, because only universes where it is finely tuned can host observers like us. For decades, this was treated as a cop-out. Physics shouldn't need to explain itself by saying, well, we wouldn't be here if it weren't this way. It was considered an admission of defeat, a place you went when you had stopped trying to find a real explanation. Now, it is proposed openly in talks at the highest levels of theoretical cosmology, including by physicists who would have rejected it as nonsense 15 years ago. The change has happened quietly. There was no announcement. The boundary between physics and metaphysics has shifted. The multiverse is the natural companion to the anthropic principle. If anthropic selection is a real explanation for the cosmological constant, then there has to be a population of universes from which selection can occur. Eternal inflation, the string theory framework, with its 10 to the 500 possible vacuum solutions, the many worlds interpretation of quantum mechanics, each of these provides a different mechanism for producing the population. None of these mechanisms is confirmed. The fact that they are now working hypotheses, discussed in journal articles and conference talks, is what has changed. Modified gravity is a third example. The idea that the equations of general relativity are wrong at galactic and cosmological scales used to be a hostile minority position. The most famous version, MOND, or modified Newtonian dynamics, was treated with open scorn by mainstream cosmologists for decades. Today, modified gravity theory's MOND, its relativistic completion TeVeS, the more recent MOG, alternatives like emergent gravity, proposed by Eric Verlinde, are studied seriously by mainstream researchers. The reason is not that modified gravity has had a breakthrough. The reason is that the alternative adding two unknown ingredients, dark matter and dark energy, to general relativity in order to make it fit the data, has lost some of its claim to elegance. When both options look ugly, neither has the monopoly on respectability. The simulation hypothesis is on a longer leash, but it is also no longer entirely outside the conversation. Nick Bostrom proposed it seriously in 2003, arguing on probabilistic grounds that if technological civilizations can simulate ancestor universes, the number of simulated minds will eventually exceed the number of biological minds, and any given mind should statistically expect to be in a simulation. Some physicists, notably Seth Lloyd at MIT, have explored the idea that the universe is fundamentally a computation, with the discreteness implied by certain quantum gravity proposals looking suspiciously like pixelation at the Planck scale. I want to flag clearly that this is speculation. There is no experimental evidence. The point is that some serious physicists will engage with it now, where they would have refused to 30 years ago. There have been a few attempted tests, mostly proposed rather than performed. One idea is that if the universe is a simulation running on some kind of finite computational grid, the speed of cosmic rays at the highest energies might show a subtle cutoff or anisotropy, reflecting the orientation of the grid. The data is too noisy to confirm or rule this out. Another idea is that very high-precision tests of the equivalence principle, whether all forms of mass energy fall in the same way under gravity, might show simulation-induced violations. So far, no violations have been found at the precision we can reach. The honest summary is that the simulation hypothesis is, at present, not directly testable. Its presence in the conversation is more about the imaginative permission the field is granting itself than about an experimental program. Roger Penrose's calculation deserves its own mention here. Penrose, an Oxford mathematical physicist who won the Nobel Prize in 2020, has long argued that the initial state of the universe was fine-tuned to an absurd degree. The number he calculated for the probability of the universe starting in the low entropy state we observe is 1 part in 10 to the 10 to the 123. Let me spell out what that number means. 10 to the 123 is a 1 followed by 123 zeros. 10 raised to that number is genuinely unwritable. You cannot represent it using all the matter in the observable universe. Penrose argues that this fine-tuning is so absurd that something is missing from our story. Either there is a principle we have not discovered that selects the universe's initial conditions, or there is a process that makes such fine-tuning natural, or our description of the initial state is just wrong. The standard response to Penrose's number is to invoke inflation. The inflationary picture of the early universe says that a brief epoch of exponential expansion stretched any initial irregularities to scales much larger than what we observe, smoothing the universe and giving us the low entropy starting condition that the second law of thermodynamics requires. Inflation works mathematically. It also produces, as a side effect, the seeds of large-scale structure that the cosmic microwave background reveals. It is the explanation most cosmologists hold to. But inflation has its own problems. There is no consensus on what field drives inflation. There is no consensus on how inflation ends cleanly. There are critics within the field, including Paul Steinhardt, who originally helped develop inflation and has since become one of its most vocal opponents, who argue that inflation is not falsifiable in any practical sense, because for any observed feature of the universe, some version of inflation can be constructed to predict it. The inflation that explains Penrose's number may itself be a problem we have not yet faced honestly. A few other anomalies deserve a brief mention before we close this section. The cosmic microwave background, the same light source that gave us the early universe Hubble constant, also contains some peculiar features that the standard model does not explain. There is something called the axis of evil, an alignment of the largest scale temperature anisotropies that should not exist in a statistically isotropic universe. There is the cold spot, an unusually large and unusually cold region of the cosmic microwave background, far larger than the standard model predicts should exist by chance. These anomalies might be statistical flukes. They might be artifacts of foreground contamination. They might be bruises from collisions with other universes, which is the suggestion some theorists have offered. The fact that the suggestion has been offered at all, in major journals, is what I want you to notice. What you should take from this section is not a specific belief about which fringe idea is true. What you should take is a sense of how the field has reorganized itself around the breaking standard model. The fringe has expanded. The respectable center has shrunk. The boundary between the two has blurred. This is what a paradigm shift looks like before the new paradigm arrives. And now I want to close the loop. What does the whole picture look like if you stand back? What is the situation, in plain language, as of 2026? That is the last thing I want to say to you, and it is not what you might expect. Is less than break time equals 1s is greater than number, part 12. The quiet possibility. Let me stand back. Step outside the field for a moment. The picture we have assembled across the last almost 2 hours looks like this. There are 6 independent fronts on which the standard model of cosmology is failing. The Hubble tension at 5 sigma, confirmed to 1% precision in April of 2026, with no remaining systematic explanation. The S8 tension between cosmic microwave background predictions and weak lensing measurements at the level of 2 to 3 sigma. The James Webb early galaxies, with their stellar masses higher than the Standard Model predicts, partly walked back, but still puzzling. The DESI signal for evolving dark energy at 3 to 4.2 sigma depending on combination. The cosmological constant problem, the worst prediction in the history of science, made even harder by the DE-psi, hint that the wrong constant is also not constant. And the dark matter direct detection nulls, 4 decades of careful experiments, finding nothing where the field had spent 50 years expecting to find a specific kind of new particle. On the other side, the Standard Model of particle physics is incomplete in known and unfixable ways. The hierarchy problem, the naturalness problem, the absence of supersymmetric particles where they were expected, the lack of unification with gravity, the lack of an explanation for dark matter, dark energy, neutrino masses, or matter-antimatter asymmetry. 2 recent anomalies, the muon G2 result, the W boson mass, have walked back into agreement with the Standard Model. They show what success looks like. They show what the field hopes for. They are, by contrast, what makes the cosmological tensions look so serious. The cosmological tensions are not walking back. They are growing. The sociological response is the calibrated speech I described. Calm press releases, worried corridors. The language drifting from discrepancy to tension to crisis without ever quite arriving at the word out loud. The Fringe has expanded into the respectable conversation. Anthropic selection, multiverses, modified gravity, Penrose's number, the arrow of time, even the simulation hypothesis. None of these are confirmed. All of them are now considered. The respectable middle ground has narrowed. This is, I want to say carefully, what every great moment in physics has looked like from the inside. The mid-1800s, when Maxwell's electromagnetic theory was breaking classical mechanics in ways that nobody quite understood until Einstein. The end of the 1800s, when the Michelson-Morley experiment and the blackbody radiation problem were small clouds in Kelvin's clear sky. The 1920s, when Schrödinger and Heisenberg blew the doors off determinism, every time, the warning signs were ignored or dismissed for years before the new framework arrived. Every time, from the inside, the people living through it did not know which clues were the important ones until the synthesis was already in progress. The present moment might be that, or it might not. There is genuine humility in the honest answer. We have models that explain a great deal. They are simultaneously breaking on multiple fronts. The next framework, if there is one, has not arrived. We are, all of us, standing in the gap. If I had to speculate about what the next framework looks like, I would not say I know. I would tell you what the candidates are. Maybe quantum gravity. String theory keeps trying, with the Swampland program finally hinting at constraints that could be testable. Loop quantum gravity has been working steadily for 30 years. Asymptotic safety, causal set theory. Each is a serious attempt. None has produced an experimental prediction that the universe has ratified. Maybe the answer is none of these, and the framework that arrives in 50 years is something nobody has yet named. Consider the historical pattern. The theory of relativity was not predicted by anyone before Einstein published it. Quantum mechanics was not predicted by anyone before the early 1900s, when a generation of physicists collectively stumbled into it. The 2 great frameworks of 20th century physics arrived suddenly, from people the old guard would not have expected, in forms the old guard would not have predicted. The next framework, whatever it is, will probably do the same. It will arrive in a form we cannot currently imagine, from a person we cannot currently name, addressing a problem we have not yet articulated correctly. That is what paradigm shifts look like from the inside. They look like nothing for a long time, and then they look like everything in retrospect. Let me name a few specific lines of inquiry that might matter, even though none of them is a confirmed answer. The information-theoretic approach to gravity, pioneered by Ted Jacobson and developed by Eric Valindi, asks whether gravity itself is a thermodynamic phenomenon emerging from underlying information dynamics. If true, gravity is not a fundamental force, but an emergent statistical effect, like temperature. The ADS CFT correspondence, discovered by Juan Maldacena in 1997, hints at a powerful dual relationship between gravitational theories in higher dimensional spacetimes and quantum field theories on their boundaries. Some physicists believe the correspondence is telling us that spacetime is a hologram, an emergent representation of information stored on a lower dimensional surface. None of these ideas is currently testable in the laboratory. All of them are taken seriously by people who have spent careers in the field. Maybe the deeper answer is that some of our most basic assumptions are wrong at a level we have not examined. Maybe spacetime is not fundamental. Maybe causality is emergent from something more primary. Maybe the laws of physics are not the same at all times, and the constants are not constant, and the universe is not a single fixed model, but a process whose rules evolve along with its contents. Each of these has at least one serious research program behind it. Each is currently unverified. Each would, if confirmed, change everything. There is another possibility I want to leave room for. The synthesis, when it arrives, might not look like any of these proposals. The framework that explains the Hubble tension, the evolving dark energy, the cosmological constant problem, the dark matter direct detection nulls, and the hierarchy problem might be a single insight that simultaneously resolves all of them. Such an insight would be revolutionary in the original sense of the word. It would change not just our answers, but our questions. And it would render most of the current debates around the cosmological tensions retrospectively quaint, the way Maxwell's equations rendered most pre-Maxwell debates about electricity and magnetism quaint. We are, in this picture, having conversations that will look obsolete in 50 years. That is not a critique of the conversations. It is what every productive moment in pre-paradigm shift physics has looked like. I want to be honest about one more thing before I close. The reframe of all this, the version I want to leave you with, is not despair. It is not panic. It is the recognition that we happen to be alive at the most interesting moment in fundamental physics since the early 1900s. A generation of physicists is living through the death of a paradigm without knowing what comes next. From the outside, in 50 years, it will look obvious which clues were the important ones. From the inside, right now, it does not. We can see the cracks. We can name them. We can publish papers about them. We cannot yet say what the answer is. That is the honest state of the field. If you have stayed with me through this, you now know more about the actual condition of fundamental physics than most people who follow science news casually. You know the names of the tensions. You know roughly what the sigma values mean. You know the sociological reasons for the public quiet, and you know that the quiet is not a conspiracy, but a structural softness in the language of a field that does not yet know how to talk about itself. You know that the universe is, by every available measure, stranger than we are currently capable of saying out loud. This is, I think, a kind of gift. Most of the things we believe about the universe are things we have inherited. We did not measure them ourselves. We did not check the work. We took them on the authority of the people who did the work, and the people who taught those people, and the people who taught those people. That chain of trust has, in the case of fundamental physics, been mostly reliable for a long time. But the chain is also a chain. Every link rests on every other link. When a link starts to bend, the whole chain feels different. What you have just spent 2 hours doing is feeling the bend. The chain has not broken. The links are still there. They are simply not, at the moment, holding what they used to hold. That is information. It is the kind of information that helps you read the news about physics without taking it at face value. It is the kind of information that makes you a slightly more thoughtful citizen of the universe. I want to leave you with one closing observation. The universe was here long before us, and it will be here long after. Whatever rules it actually runs on are the same rules it has always followed. Our models were always going to be incomplete. The only question, ever, was when we would discover that, and how. The answer to when, it seems, is now. We are simply the generation who happened to be here when the cracks started showing. The cracks are not the failure. The cracks are the signal. They are the data telling us where to look next, in the patient way that data has been telling us where to look since the first careful astronomer noticed that the planets did not quite move where the Ptolemaic model said they would. Every time the model has broken, the breaking has been the door. Copernicus did not invent heliocentrism by accepting the model of his time. He invented it by taking the model's failures seriously. Kepler did not derive the elliptical orbits by trusting circles. He derived them by trusting Tycho Brahe's data more than he trusted the existing geometry. Newton did not write the Principia by extending Aristotle. He wrote it by starting over. The pattern is older than any of us, and the pattern is honoured by paying attention to the cracks. The universe is not breaking. Our description of it is. And every previous time that has happened, what came next has been larger and stranger and more genuinely beautiful than what came before. We do not yet know what it will be. That is the part that is mysterious. That is the part that is, in its own quiet way, the most exciting thing in the world. Sleep well, knowing that the universe has been here for 13.8 billion years and is in no hurry to resolve itself for our convenience. Whatever the answer is, it has been here the whole time, waiting for us to ask the right question. We are only beginning to ask. The asking has barely started, and the strangest, most unexpectedly tender truth in all of this is that we get to be here for it.